You know, we think of science as this powerful searchlight, always uncovering the truth. But what if I told you that sometimes science misses things that are right in front of its nose, not because of bad intentions, but because the tools themselves have a blind spot? Today, we're going to dig into a really cool 1994 paper that found one of these blind spots and basically gave researchers a new pair of glasses. It all starts with a question we ask ourselves all the time. Does one size really fit all? I mean, think about it. Does a new drug work the same for every single person? Does a new teaching method have the same effect on a 6-year-old as it does on a 16-year-old? Deep down, we kind of know the answer is almost always no. What's a game changer for one group might do nothing for another.
So, let's get into how scientists officially tackle this. How do they ask that one-size-fits-all question? Well, they frame it as the "it depends" question.
And that crucial "it depends" factor, it has a scientific name, of course. It's called a moderator variable. That's the key. It's the thing that can completely change the relationship between a cause and an effect. It's the reason the answer to so many complex questions is, well, it depends.
Let's make this real. Go back to that teaching method. So the claim is it improves test scores. But what if it only works for younger students? For them, it's amazing. But for the older ones, it does nothing. The success of the method depends on the student's age. And right there, age is your moderator variable. It's the whole story. Okay, so how do scientists actually go looking for these things? Well, as this 1994 paper points out, they often look for something called dichotomous moderators. Now, don't let the fancy word scare you. It just means things that fall neatly into two groups. Think male versus female, or a group that got a treatment versus a control group. And for decades, the standard tool for this job was a statistical technique called Moderated Multiple Regression, or MMR. So you've got the question, you've got the tool, problem solved, right? Well, not so fast. Because, as it turns out, that go-to tool had a pretty big hidden flaw. The authors of the paper just laid it right out there. They found that these critical searches for "it depends" factors were often being done with, and here's the key phrase, low levels of statistical power. And this wasn't just a small issue. It was a quiet, massive problem hiding in plain sight. This brings us to the absolute heart of the matter. It's a term you hear thrown around a lot in science, but what does it really mean? What is statistical power? To really get our heads around this, let's use an analogy. Imagine you're a detective. You're in a huge, pitch-black warehouse, and you're searching for a single tiny clue. Your success is going to depend entirely on one thing: your flashlight. Statistical power is basically the brightness of your flashlight. A study with high power is like having a giant, powerful searchlight. You can blast light into every corner, and if that clue's in there, you are definitely going to see it. But a study with low power, that's like using one of those weak, flickering keychain lights. You could be standing right next to the clue and completely miss it because it's just outside your tiny little circle of light. And this, right here, is the huge danger of low power. A researcher with that dim flashlight might search the whole warehouse and conclude, well, there's no effect here. The clue doesn't exist. But the truth might be that the effect is absolutely real. Their tool just wasn't strong enough to see it. They're mistaking "I couldn't find it" for "it isn't there." That's a massive difference. Now, this wasn't just a feeling. There was a hard number, a benchmark established by the famous statistician Jacob Cohen. A good study should aim for a power level of 0.80. That gives you an 80% chance of finding an effect if it's real. The trouble was, tons of studies searching for these moderators were falling way, way short of that standard. So researchers were walking into dark rooms with dim flashlights over and over again. But this 1994 paper didn't just point out the problem. It actually gave everyone a way to fix it. The lead author, Herman Aguinis, and his team did something so wonderfully practical. They didn't just write a paper saying, this is a problem. They built a tool. This paper wasn't just an academic argument. It was basically a user's manual for their invention. And their solution is so perfectly of its time, you gotta love it. It wasn't some crazy complex software. It was a simple computer program written in Quick Basic. I mean, we are talking about the era of those big, beige, IBM-compatible PCs. And how did you get the program? You could literally mail the authors and they'd send you a copy on a 3.5-inch floppy disk. It was all about making it accessible. So how did this little program work? It was brilliant in its simplicity. First, a researcher would just punch in the details of the study they were planning to do, like how many people they'd have.
Second, the program would run a quick simulation and estimate what the study's statistical power would be. And third, this is the magic part. It would tell the researcher exactly how bright their flashlight was going to be before they even stepped into the warehouse.
This little program gave researchers the power of foresight. No more flying blind. Once you could see your estimated power level right up front, you could make a smart choice. You could either go back and improve your study design, maybe get more people to participate, or you could move forward, but at least you'd know you were working with a pretty dim flashlight and be cautious about your conclusions.
A quick basic program on a floppy disk? Yeah, it might sound like an ancient relic, but the lesson it taught science is actually more important today than ever before. So what's the big picture here? Well, first, that good science isn't just about having a great question, it's about making sure your tools are up to the job. And second, and this is so important, finding no effect is not the same as proving there is no effect. All it might mean is that your flashlight was too dim. This simple program from 1994 really forced a crucial conversation in research, and it helped make sure those vital "it depends" factors weren't being missed anymore. And that leaves us with a pretty provocative thought to end on. It kind of makes you look at science differently, with a bit more healthy skepticism. It makes you ask, how many of the things we accept as scientific facts today are simply the result of someone searching with a dim flashlight? How many incredible discoveries are still out there, just sitting in the dark, waiting for someone to finally show up with a flashlight bright enough to see them?